This program is about buying a house. Now we're going to tell the story in two parts. In the first part, we're going to develop a mathematical model which you can use to determine how much your monthly mortgage repayment should be. Now this model turns out to be a recurrence relation. And in the second part of the program, we're going to have a look at some of the aspects of recurrence relations. And in particular, we're going to have a look at the problem of ill conditioning. Well, the story starts with buying this house. It's quite a snip, it's got all mod cons, and it's on the market for £30,000. Now, of course, you tend not to borrow all the money you need to buy a house. Some of it will come from selling a previous house, or it might come from your savings. In any case, building societies have an upper limit on what they'll lend you. Well, for this house, let's suppose that we've got £10,000 of our own. That means we'll have to borrow £20,000. Well, the question is, how are we going to pay that back? Now, that's the problem that we're going to tackle in the rest of this program. How can we get mathematics to help us to solve this problem? Well, that's where modelling comes in. Modelling is something that you'll see throughout the course. It's a technique which comes in various stages. And at the moment, we're at the stage of examining the problem. Now, it's worthwhile pointing out at this stage that we've left a lot out. We've ignored such things as solicitors, surveyors, estate agents, and so on. These are just complications that would get in the way. It would clutter up our model. So our first piece of advice to you is, at least at the beginning, keep it simple. Now, one of the ways of keeping things simple is to look at just one kind of mortgage. We're not going to look at endowment policies or anything like that. Our problem is where we repay the mortgage gradually paying off the amount that we've borrowed. Now remember, that's £20,000. But we're going to need two more pieces of information. The first is, how long are we going to take to pay off the mortgage? Second, how much are we going to pay? How much interest do we have to pay just for the privilege of borrowing? Well, 25 years is a typical length of time to take. And I dare say that in times of rapidly changing interest rates, 15% seems like a bargain. So let's accept these figures, buy the house, and start paying back. Well, to see how much we pay back, we're going to have to build up a mathematical model. And that's where Mick takes over.
To get the model, you have to understand how the repayments work. And to do this, we're going to look at what happens in the first year. Now, you start out owing £20,000. But right away, the building society adds on its interest, which is 15% of £20,000 or £3,000. So, before you've paid anything back, you're in debt to the tune of £23,000. Now, the building society requires you to pay back a fixed monthly sum. And the problem is to work out what this is. But for now, let's take the building society's figure. In this case, it's £258. Okay, so subtracting £258 off each month, we get, in February, £22,742. In March, £22,484, and so on. Now, by the time we get to November, we're down to £20,420, and in December, £20,162, and that's still more than you started out with. But the final repayment of the year makes the first dent in our mortgage, and we start the new year owing £19,904. And that's just £96 less than you started out with. But now it's interest time again, and we have the 15% of £19,904 to add on. And this is £2,986. So we now owe £22,890. Now this is no way to pay back a mortgage. If you only pay back £96 a year, it's going to take you over 200 years to pay it back. But you can see that we do owe a little less now, so with the same repayments, we'll make a bigger dent in the mortgage next year and progressively bigger dents in succeeding years.
So, paying back £258 every month gives us these figures. And you can see that in the first year, the amount that we'll be owing is £19,904. So in fact, we've repaid £96. In the next year, the amount owing has gone down to this, which means that the total repaid is now £206. And you can see that as time goes by, the amount owing decreases, and of course the capital repaid increases. Now, these figures will depend on that monthly repayment of £258. Now, how did we get that figure?
This is the process that we've been going through. The amount that we owe this year, plus the interest, minus the 12 repayments, that's exactly the amount that we owe next year. Now, we have a relationship between what we owe this year and what we owe next year, and that's going to give us a recurrence relation. Now, if we let UR be the amount that we owe this year, then the interest is just 1/1500 of UR, and the repayments, well, so that we can work out what the monthly repayment is, we'll call it M. And since we make 12 of these, we're going to subtract off 12M. And this is just the amount that we owe next year, which is UR plus 1. And so we have the recurrence relation, UR plus 1 is equal to UR plus 1/1500 UR minus 12M. And we can simplify this to write UR plus 1 is equal to 1.15 UR minus 12M. And this is going to be the model for our problem. Now, it only involves UR plus 1 and UR, so it's first order. And it's a constant times UR, so it's linear. And this minus 12M here means that it's non-homogeneous. And using the techniques in the text, we can solve it.
Solve it? What do we mean by that? Well, it means getting a formula like this one. And what this enables us to do is to compute these values down here without having to have previously computed all the earlier ones. Now, this formula expresses the amount owing in year n. And to find that value, all you have to do is to substitute the value of n into the formula. Now, you'll see that as we get this formula, we'll also find that the monthly repayment has to be £258. Well, how do we get that formula?
The solution of a linear first-order recurrence relation is made up of two parts. It's the sum of the solution to the homogeneous problem plus any particular solution of the non-homogeneous problem. So if we write down the recurrence relation, we want the homogeneous relation, and we get that by ignoring the 12m. Now the solution of this is just un is equal to some arbitrary constant b times 1.15 to the n. So that's the first part of our solution. For the second part of our solution, we need any particular solution of the non-homogeneous problem. And the simplest solution to this non-homogeneous problem is just of the form un is equal to a constant. Let's call it k. And if we substitute that into the recurrence relation, we get k is equal to 1.15 k minus 12m. And after some arithmetic, we end up with the value k is equal to 80m. Okay, so the solution, the general solution to our non-homogeneous problem consists of the general solution to the homogeneous problem plus our particular solution, which is 80m. Now, this solution involves two unknowns, b and m. And we need two extra conditions in order to get the formula that Pete had earlier. Now, what pieces of information do we have? Well, we know that the initial value, U0, the mortgage we started out with, was £20,000. So we write U0 is equal to 20,000. And after 25 years, we should have paid it back. This gives us U25 equals 0. Now, using these two values in this formula, we get two simultaneous equations for the values of b and m. Now, I'm not going to go through that here. The values you get to the nearest integer are b equals minus 626 and m equals £258. Just like the Building Society got it.
Well, not quite. If any of you have a £20,000 mortgage at 15% over 25 years, don't complain to the Building Society just yet, because there's still one important stage of the modelling process we haven't done. And that's comparing the predictions of our model with reality. And as a result of this comparison, we may well have to re-examine the problem again and go round this cycle of events. This time taking into account the things that we left out before, like surveyor's fees, solicitors, insurances, and so on. Now, we're not going to do that here. Instead, we're going to check the figures that our model gave us. Now, remember what our model was. It's this recurrence relation together with the initial value U0. Well, one check we might think of is to see whether our model does in fact pay off the mortgage after 25 years. What we want is for this column to go to 0. And in particular, we want U25 to be 0. Well, this is U25, and the minus sign says that we've paid off too much. We've overpaid by £427. So what's wrong? Is the model incorrect? Well, no, it's not, because we've glossed over something. When Mick found the 258, we didn't do the calculations exactly. That figure, a more accurate figure, should have been 257.832 something. And what we did was to round that up to the nearest pound. So effectively what's happened is that we've overpaid by 17 pence every month. And that, together with the added interest, has accumulated to give us this discrepancy. Well, almost, because there is yet another source of error. the amount of interest added each January was also rounded to the nearest pound. Well, do these errors matter? Isn't the model good enough as it stands? Well, yes, it is good enough. After all, a building society can quite easily take these discrepancies into account by having, say, one special payment right at the very end. Well, that's the end of the first part of our program. That's the modeling completed. Well, we've got a model. How can we use it? Well, let's suppose the interest rate changes, as it quite often does.
Now, this is where being familiar with mathematics will give us some idea of what to expect. The problem of calculating UN using this recurrence relation is ill-conditioned. Absolutely ill-conditioned. And it's this 1.15 here that's the culprit. In problems of this type, if this factor before the UR is greater than 1, then we get absolute ill-conditioning. Now, what does that mean? Well, it means that a small error in the data, and that's the £20,000, or this 1.15, or this £258, then those errors will grow during the course of our calculations. And we've seen that already. A simple rounding in our repayment led to an overpayment of £427 after 25 years.
Well, all the figures that you've seen before were all produced by computer. And what we're going to do now is to see what happens when we up the interest rate. Well, the smallest practical increase is 1/4%. So let's see what happens to the figures if we keep paying back the same monthly amount of £258. Now remember, the Building Society may not in fact let you do this, but you've been warned. This problem's ill-conditioned. A small change is going to have a large effect. At 25 years, you still owe almost £10,000. And in fact, you'll find it'll take until 30 years to completely repay the mortgage.
Absolute ill-conditioning can be troublesome, but there's something else about this problem. For the data we're using, it's also relatively ill-conditioned. Now, what does that do for our mortgage?
Well, let's have a look at the effect on the figures. The effect shows up after just another 1/4% rise in the interest rate to 15.5%. As you can see, the effect is shown up after just 1 year. You've ended up owing more than you started with. And it's going to get no better. What's happening?
What's happening is that everything's changed. The mortgage isn't behaving at all like it did before. And to see this, we need pictures. Let's look at our 20,000 mortgage over 25 years. Year by year, the amount owing decreases until we hit 0 in year 25. It's easier to see this if we draw a smooth curve through the points. Let's leave the 15% mortgage there and see what happens at 15.25%. It takes longer, but it's the same shape. Starting at 15% and changing the interest rates, we get curves all of the same basic shape, but only while the change stays below this value. two larger chains, and the curve flips over, and we get a complete change in the behaviour. And in this sort of problem, it's the relative ill-conditioning that's responsible. For small changes in the interest rates, from 15 to 15 and a quarter to 15.4, we get large changes in the values. That's the absolute ill-conditioning. We start out when we owe approximately £20,000 with a flat shape, but it gradually steepens as we pay the mortgage off. But if the rate increases a little bit further, the curve completely changes. It starts off being flat, but then steepens upwards. And in between, there's this particular value, where the £258 merely pays off the interest.
Well, it's pretty obvious that if you don't pay back enough each month to cover even the interest, then you're going to get into trouble. And our study of ill conditioning has shown that for our problem, we're in an area where dramatic things can happen. Now I wonder whether our knowledge of ill conditioning can actually work to our advantage. Well, let's go to the model. It doesn't look as though we can change very much here. After all, the interest rate is set by the building society. The amount you borrowed, well, that's merely a matter of history now. And the amount you pay back each month, £258, well, that looks pretty fixed as well. But there is just one thing you can do. Nobody's going to prevent you from paying back more than the £258 a month. Well, common advice is that you shouldn't do this. Staying in debt for a long period can be an advantage, especially with high interest rates, tax relief and what have you. But if your objective is to pay off your mortgage as quickly as you can, then perhaps finding just £5 more every month will pay off that mortgage more quickly. Now remember, this problem's ill-conditioned. When do you think the mortgage will be paid off?